Right. So we looked at the homogeneous linear system. So I'm just going to go through the main idea on how to find the solution. So we have a homogeneous system that we have right there. And the question is, how do we get to find the solution of the system? So we then now have this solution vector form e to the power lambda t, where k here we'll call it the agent vector, and the lambda is actually an agent value. So we then now say this is the trial solution and plug it back into the homogeneous system and find the values, the vector k and the values of lambda that satisfy the system. Okay, so if that is the case, we just need the derivative and go back to the homogeneous system and just substitute our trial solution into it. If we do that, we then realize that e to the power lambda t is a function is not equal to 0, and then it remains with ak. I just had to rewrite ak is equals k lambda I. Just to maintain the dimension of the matrix, we multiply by an identity matrix. So this is an identity matrix, which is the same dimension as A, which is n by n in this case. So after doing some algebra, we end up with this system, a matrix equation, where now this matrix equation is what? Is 0 equal to 0 vector. Now, to find the solution of the homogeneous system, which is labeled as 1, we want k, the agent vector, to be non-trivial. In other words, k is not a 0 vector. K is not a 0 vector, by just saying k is non-trivial. K is not a 0 vector. So not all the entries of k are 0. Okay. So if then k is not a 0 vector, then we are forced to then make the coefficient of k to be 0, and that can only be defined in terms of the determinant, or you can write it like this, equal to 0, and we'll then call this the determinant of a minus lambda equal to 0. We call this the characteristic equation. So the characteristic equation's role is for us to find this unknown. A is known, is given, and I is known as an identity, so it's given. So what is not known are the lambdas. So this equation allows us to find the lambdas, or the agent values of the coefficient matrix. Okay, so that's what it is. And with this matrix that is a n by n, when we find agent values, we are bound to find n of them, n lambdas. Because the n by n, it should give us n lambdas. Now, these lambdas could have different cases. So the two first broad ones is lambdas could be real valued. They're real numbers. Or lambdas could be complex valued. They are complex conjugates. Okay. So then we are going to explore this. What happens when we have real valued eigenvalues? What happens when we have complex valued? So we'll start exploring this part. So if A has n distinct eigenvalues, it means they are different, they are real valued, right? So we can have the first case of real valued eigenvalues as lambda 1 up to n up to n, where lambda I is not equal to lambda j for I is not equal to j, and I j 1 less than 1 less than ij less than n. Okay, so it just says there are no two eigenvalues that any two eigenvalues or that are equal, and any all of them are different. There are not any two eigenvalues that can be the same. Okay. So now what will happen is associated with each eigenvalue, we have a unique eigenvector. Remember, our x is a vector. We said it's k in the power lambda t. So we then have solutions now. X1 is equals to k1 in the power lambda 1 t. And up to xn is equals to kn e to the power lambda nt. And these are solution vectors, n of them. So, and these eigenvectors are linearly independent. Then we can then now use the general solution as using the Fanda's superposition principle. The superposition principle to then find a linear combination of all the n vectors, solution vectors, and these c's are actually constants of integration. They can only be found after you specify the initial conditions. So you start by finding the general solution, then you can then apply the initial conditions to find these c's. Okay, so let's look at this example here. So 2 by 2 is a linear system, you can tell, and you can write it in matrix form. 2, 3, 2, 1 times xy, all right? 2, 3, 2, 1 times xy. So you can identify your coefficient matrix. So first of all, you have to find the eigenvalues and the associated eigenvectors, okay, of A. So the matrix of coefficients is given, and we then create the determinant of the characteristic equation to form the characteristic equation of the matrix A minus lambda I. And when we do that, we get this determinant here and then equate it to 0. And you can see it's a quadratic. So if you simplify it, you can then refactorize it and find that you have lambda is equals to -1 and lambda is equals to 4 as the two eigenvalues. And you can see they are real values and they are distinct. So we have a case of distinct eigenvalues. So now we need to find the associated eigenvectors. So because A is a 2 by 2 for matrix, then K, all the eigenvectors will have a 2 by 1 dimension. So we go back to this system, and this, remember, this is now a 0 vector. So associated with lambda 1, we are just saying solve the system A minus -1 I times K1, K2 is equal to the 0 vector, which then says you have A plus I times K1, K2 is equals to what? The 0 vector. All right. So solving that system is just as good as solving the augmented matrix with 0, 0 here. But there's no need of putting the 0, 0 because it doesn't change anything. So you end up just using A plus 1 by A plus I, and then do raw operations until it is in reduced form, until you can find K1 and K2. So you can then see to it that this gives us this matrix here. And Here I did not, so I used the row operations. Row 1 goes to 1 over 3 row 1, and row 2 goes to 1 over 2 row 2, and then the same row 2 that has been transformed now will go to row 2 minus row 1. And if you do these three operations, you end up with this guy. So what it means is one of the variables K1 and K2 is arbitrary. But because the zero vector is on the second row, we then say K2 is arbitrary. In other words, we can say K2 is equals to some other parameter R. But on the first row, we now have K1 is equals to minus K2. So if we had called K2 R, then K1 will become minus R. So that when we combine now a K1, K2 to form our eigenvector, we have minus R, and we can factor out R. And at the end of the day, the most basic one is found by just letting R, for example, equal to 1. Yeah, you can make R any number, but usually you just choose something that makes life easy to maintain this as our eigenvector. So we now have K1 is associated with lambda is equals to 1. And from there, we know that x1 as a solution vector is then equal to minus 1, 1 e to the power minus x or minus t. Whatever the case might be, what are we using? We're using x, isn't it? Yeah. Okay. So that's what we are going to have. Then we go to lambda is equals to 4, and we are going to see that this uh, matrix will then now reduce to that matrix there. And you can just do row 2 goes to row 2 plus row 1, and you are done. So you can now see that K2 will remain arbitrary, and then K1 will be 3 over 2 K2, and which is just 3 over 2R, something like that. Then when you then build up the second eigenvector, this is capital letter K. The others are small letters. They're small letters. So the capital letter K, which is the eigenvector associated with lambda is equals to 4, will be like this. So now you could still say R is equals to 1 here and get this as the eigenvector. But you could also say, I don't like fractions. So for me to get rid of the fractions, I'll just say R is equals to 2 so that this half will disappear. But when I do that, I get now this eigenvector that is what? Associated with lambda is equals 4, but without fractions. But you can still leave it with fractions. For some, they have challenges working with the fractions, so they would rather work with the whole numbers. So it's neither here nor there. What you then need to know is the eigenvectors are not necessarily unique. Okay, so there we are. And then we have our solution vectors x1 and x2 associated with lambda 1 and lambda 2, and k1 and k2 is the eigenvectors. And we then now use the principle of superposition to get the solution. All right. So this is for a 2 by 2. You can do it for a 3 by 3 and a 4 by 4, n by n. And you then need to verify that one, the K1 and the K2 are not trivial. They are not necessarily words or origin vectors. You can also verify that K1 and K2 are linearly dependent. So just take the Wronskian which is just taking the vectors themselves and put them as columns. And if you look at this, this will be -2, -3, which is -5, which is not equal to 0. So K1 and K2 are what? Are linearly independent. So then X1 as a solution vector and X2, they form the fundamental set of solutions to the homogeneous system, the linear system that we were dealing with. And this becomes now the general solution of the equation. All right. If we want to get the xy, so this will be x, this will be y. Separately, see now they are a linear combination of e to the power minus t and e to the power of t. It's up to you. But once you are here, you are still okay. It's just expanding this to get these two separate solutions for x1 and x2. Okay, let's look at a 3 by 3 system. And this is linear and homogeneous. So all we do is to collect the coefficients. So all terms associated with x are going to be put under the same or the first column. All terms associated with y, they're also going to be put the second column. And all terms associated with z, they are also going to be put under the same column. And there we are. We have the third column, sorry. So there we are. We have our coefficient matrix. So what we need now is find the eigenvalues. So when you do this, sometimes it's nice to just go for the row with most zeros. But you then, for the minus, you then have to follow this plus, plus, minus, plus, minus, plus. No, this is minus, plus, minus, plus. So if I use that, I'm then going to say this is equals to 0 or plus 0 or minus. So the 0, 1, you're multiplying by 0, so you leave it. So you then have minus 1 times the minor. So we leave this, it will be -4 minus lambda, and then 1, and then 1, and -1. Then plus, which is now -3 plus lambda times the minor -4 minus lambda, 1, 1, 5 minus lambda is equal to 0. So it reduces the number of computations you can do. There's no use to use row 1 when later you will see that you are just carrying, one of them is just carrying a 0. So go for the rows with most zeros, and then do the expansion of the determinant when you're using the coeffective expansion. So then it will then now lead you to get this a factorized system here where these are your three eigenvalue values. And you can see that they are all real valued. They are all real valued. So you then now go through the same process. Associated with each eigenvalue, you're going to solve for an eigenvector. So do the row operations here and see to it. So what are the row operations? So here it says row 1 goes to minus row 1, just to have a leading entry, which is what? Which is 1. And you can have, I think there's row 2 interchanges with row 3, and then row 3, you then say row 3 is, so okay, row 2 interchanges with the row 3, and then this new row 3 is then going to row 3 minus row 1. So when you've done that, then you find and many other rows. I can't remember what else can you do there. And see to it that you get to a point where now you're going to see that K2 is equal to 0, and then K1 is equals to K3. And if you call K3 is equals to R, then you are going to have your first eigenvector being 0, 1, 0, 1. You do the same associated with the lambda is equals to minus 4. And this is the augmented matrix. I have put the zeros here so that you get used to it, but there's no need to put the zeros. Then you do all your row operations until you come to this point. So the row operations are important. You can be penalized if you don't if you don't put them. Okay. So at the end of the day, uh, you have your the row operations, and get the K2. So that's your linear algebra. That's why I'm going past it without much waiting. You do the same for lambda is equals to 5. And at the end, you also get K3 there. So you have three distinct eigenvectors associated with three distinct eigenvalues. And it should be a norm for you to verify that these are non-trivial, but also these the eigenvectors are actually linearly independent. They should not be, then the determinant should not be 0. And we can use our we can now use our the superposition principle to find the general solution. All right. So this is the first case where you are using a distinct eigenvalues associated with a distinct eigenvector. In fact, once you have distinct eigenvalues, you are always going to get distinct eigenvectors. So that's the first case or first sub-case of real valued eigenvalues of the coefficient matrix of the homogeneous system. All right, so we have now a case of a real valued. So these are still real valued, but repeated. Right. So there are two sub cases on this as well. So they're real valued and repeated eigenvalues. There are two scenarios that can come out of this. One, you can still have this lambda 1 repeated like m times, but then this lambda 1 gives you m linearly independent eigenvectors when you are finding the eigenvectors. Just one of them, which is repeated m times, leads to m linearly independent eigenvectors. Then this case is more similar to the distinct eigenvalues, because then all you will do is to then say x1 is equals to k1 e to the power lambda 1 t, and then x2 is equals to k2 e to the power lambda 1 t, up to xm is equals to km e to the power lambda 1 t. So this is a special case of repeated eigenvalues. So in this case, you have to use the same approach now, because this x1, k1, k2 up to km, they're linearly independent. It makes x1, x2 up to xn, the solution vectors linearly independent. And the general solution is just a linear combination of these two, of these n m solution vectors. So this one is more straightforward on the repeated real valued eigenvalues case. It's one eigenvalue giving us m, because this eigenvalue is repeated m times, then it will give us m linearly independent eigenvectors. And the case is straightforward, a linear combination of these uh, a, a solution vectors will give us the general solution to the superposition principle. So when an eigenvalue is repeated m times, we say it has the eigenvalue is multiplicity m. Okay, so this is the first case. All right. So now let's say we have this lambda one and it is repeated m times, it has multiplicity m, and then it only gives us k1. But remember, it is repeated m times. We are expecting to get m linearly independent eigenvectors, but now we're just getting one. So, which means we are short of m minus one eigenvectors for our solution to make sense. Because it's an n by m, n by n, and it has to balance the number of what? Of solution vectors should be n as well. So at the end of the day, we want to make sure that we recover some of this. So it's remember, just think of the case of reduction of order, where you have one solution and you need to find the other one. This is more of a similar concept here. So what we're going to do now is to find a way. Remember, with the case of single equation, the second order, we will then say if y1 is equals to e to the power uh, lambda 1 t, then the second one will then say it's equals to t e to the power lambda 1 t to find the other one through that is linearly independent and also through the method of reduction of order. So this is an equivalent kind of thing. So let's say associated with lambda 1, we have K11. It's just re-indexing for the sake of generalizing. But it could be K1 as usual. So the second one would be a linear combination of a vector K2, 2 and K2, 2, 1, but with now you multiply by T to make it to induce linear independence. Okay. And then you carry on doing that. If for x, eh, x3, you can guess that it can be k31 t squared or k32 again. Yeah, k32 t squared e to the power lambda 1 t plus k31 t e to the power lambda 1 t plus k33 e to the power lambda 1 t. And then you can generalize now as you go to what? Towards m. You can see for x2, t has power 1. For x3, t, the highest t has power 2. So for xm, the highest t has, oh, this one should be now over 2 factorial. Yes. So you then have t to the power m minus 1 over m minus 1 factorial, and it reduces the powers of t as you go until you get to the what? To the last one, which is free of t. So these kji's are actually column vectors. So we're then going to introduce how do we find k21? How do we find k22? And the rest. Uh, this one is known because that's the one that we're referring to as K1 here. So once we have that K1, it will then be used to find the rest of these Ks that are following in other solution vectors. So this is where you need to sort of pay attention because this is so special that if you lose out the method, you will never be able to solve it. The other one was really easy. So let's do it through an example. This one, solve x prime is equals to x. Right. So as usual, take the coefficient matrix And you can find that after simplification, so this is where you fill in the gaps. Fill in gaps. Make sure that you fill in gaps when you're studying this. Don't just watch it and leave it. So you fill in gaps, you get this characteristic equation, and you can find that a lambda is equals to minus 1 is multiplicity 2, and lambda is equals to 5 is multiplicity 1. So we anticipate to find a K3 here, a, a eigenvector associated with lambda equal to 5. But here we need 2 because m is equals to 2. So we want 2 associated with lambda is equals to minus 1. So let's try. The eigenvector associated with lambda is equals to minus 1. And if we do this, you can find that within just a series of row operations, we can get that 2 of these, we remember this would be some K1, K2, some K3, small letters. So you can find that K3 and K2 are arbitrary. So because they're arbitrary, they need to have two different uh, letters, T or parameters R. And then the first one will then give you that K1 is equal to K2 minus K3, which is just a T minus R. So when we assemble the eigenvector, we have T minus R. So what we can do actually here, without doing what I did there, is we can expand this to T T0 plus a minus R0 R. Or you can then say T into 110 plus R into minus 101. So then you can say T, this will then be equal to K1 and this will be equal to K2. But to get K1, you then say T is equals to 1 and R is equal to 0. Then you get K1. To get K2, you then say T is equal to 0 and R is equals to 1. But you can make other choices until you get T is equals to R is equals to 1. You can make other choices. So you can see if I did this, T is equals to R is equals to 1, I get K2, which is like this. If I say T is equals to 1, R is equals to 0, so I get this one. So depending on the choices of T and R, you can get two different combinations there. But these ones are the ones that we're using. And then we have lambda is equals to minus 1, but it's associated with two distinct eigenvectors. So this is a straightforward case where we then now have x1 as this and x2 as that solution there. And just go and say C1 plus C2x2 as the general solution of the what? Of the homogeneous equation. So this is one of the interesting and straightforward ones. We're dealing with the examples on the two cases. So this was the first case where we have repeated eigenvalue leading to directly M linearly independent eigenvectors, and we are done. And then all we need is to do the third one for lambda is equals to 5. And after doing a number of simplifications, we get K3 is equals to that. So now we have a straightforward solution, similar to the case of distinct eigenvalue. So the issue is on the eigenvectors. How many do you get? If they match the number that we are looking for, then we are done. We just create the generalization. Let's look at this guy here, the 2 by 2 matrix. Uh, let's look for the eigenvalues. So you are going to have This is 3 minus lambda times 9 plus lambda with a minus outside there, and then plus 36 is equal to 0. So a simplify this and show that lambda is equals to minus 3 is actually what? The agent the agent vector agent value that is repeated twice. Okay. And then we want to find the agent vectors now. So we have one agent value, but we need two agent vectors. And when we do this, we then find that we just have one agent vector. So the question is, where do we find the other one? Where do we find the other one? So we started with A minus lambda 1 I times K1 is equal to 0. And this is what gave us the K1 agent vector. So now to find the second one, we could just call it K P. I know in the general formulation of the agent vectors of the other solutions, we then called it K 2 2 1, something like that. But let's just call it P. So now, since we know K, we then now use K1 to find the second one, which is now called P. Let the unknown one be equal to P. So when we do that, we no longer equate to the 0 vector. We now equate to the K1, which means if we get a wrong K1, it then affects how we are going to get P. So we are now formulating this system. And of course, because lambda is equals minus 3, it gives us this system. And it's just a matter of now solving A plus 3I augmented with what? K1. So this should be K1 augmented with K1. So we found our K1. This is where you would want the agent vectors to just have real whole numbers and not fractions necessarily to avoid a lot of algebra with fractions. So then we deal with the augmented matrix and we do our row operations. So here row 1 was going to 1 over 6 row 1 and row 2 goes to 1 over 2 row 2. So we got that. And all we do now is then say row 2 should go to row 2 minus row 1. And once we have that, we can see the whole second row is 0. So what it means is K1 is equals to half minus plus 3K2, or P1, sorry, P1 half plus 3P2. So you can start doing combinations of P1 plus P2, or you would probably, yeah, you do the combinations in this case. So if you say let P1 be equals to half and P2 is equal to 0. I just put half here because I have half plus 3 times half to create a whole number. That's all. That was the choice. Or you could even have said P2 is equals to a 0 if you wanted. You could put P2 is equals to 0, and you get um, P1 is equals to half, P2 is equals to 0. Or you can say P2 is equals to half if you want. Then you would have a half plus 3 over 2, which is 2. But then you would have 2 and half here. So you could still use that. If you want, you then now say this is equals to 2 into 1. No, it can't. So you can leave it like that. So you can choose what you want. You can choose what you want. But here I chose it in such a way that, of course, I remained with the P being half and 0. And at the end of the day, I now know that x2 will be my original k1 times t e to the power minus 3t plus p times e to the power minus 3t. And this is what will give me my x2. So now I can then go back and then say c1 x1 plus c2 x2. And this is what we get as the solution. So if it was a 3 by 3, let's say lambda was repeated 3 times, we would have the first system as A plus 3i k1 is equal to 0. Okay? Then, because we have k1, we now find a second one, which is A plus 3i times p is equals to k1 to find a second one. But because it's 3 times, we'll then go on and say A plus 3i times a new one unknown q is equals to p. So it's iterative like that. So no matter how many times it's repeated, we create new unknowns based on the previous ones that we have computed. And then you then have solutions like x1 is equals to k1 e to the power minus 3t, and then x2 will then be k1, the same k1 times t e to the power minus 3t plus p e to the power minus 3t. And then the x3 now would be the same k1 will start, but t squared over 2 factorial e to the power minus 3t plus p now follows p multiplied by t e to the power minus 3t, and then plus the q e to the power minus 3t. So that's how you iterate on finding the next one. You can see they become long as you generate the next one. Okay. So this is how you would deal with the case of repeated eigenvalues, but that will only give you one eigenvector associated with them, and then you need to find the rest. Okay, so, I think this is what I was trying to illustrate in general. And we then should find for a 3 by 3 matrix these eigenvectors K, P, and Q that satisfies this system that I showed. Let's look at this example here. Look at this example. It is straightforward here that lambda is equals to 2 is actually an eigenvalue that is repeated 3 times. So let's go to our computation of the eigenvector k. We want to find the eigenvector k. And if you do your row operations, you will then now find that this one was just row 2 goes to 1 over 5, row 2. It was not necessary. This was self. You could just compute it directly. So there we are, and we can now see that a K3 is actually equal to 0, and K2 is actually equal to 0. And then K1 remains arbitrary in this case. And we only have this K100 as our only eigenvector associated with lambda is equals to 2. And we needed 3. Remember, it's multiplicity 3. Needed 3. So let's look for a vector P with P1, P2, P3, because this is a 3 by 3 system. But what we'll just do is to take A minus 2 lambda, 2i, is equals to K. So we are augmenting that system, and you would still do your row 2 goes to 1 over 5, row 2, and get there, which might not be necessary. And you might want also then to then say row 1 goes to a row 1 minus 6 row 2, and you get what you get here. Uh, just trying to make life easy for us. So it's more like going through the Gauss-Jordan process, but it's not necessarily the one. Maybe it is reduced echelon form. So here you find that K2 is equal to 1. And then K3 will be equal to 0. Then K1 will be equal is arbitrary. So once you do it like that, then you can choose even R to be equal to 0 if you want. If you want to choose R equals to 1, it's up to you to give you something different. So, but this choice gives us something that is interesting and is simple. So P is found. Now, we now need to solve for A minus 2I times Q is equals to P. So then we have an augmented matrix. So the Q would just be some Q1, Q2, Q3, and non-vector. So the augmented matrix with P, and you can do the same. Row 2 goes to 1 over 5, row 2, and you get that. And what you then see is from here, you have K3 is equals to 1 over 5. Okay? And then here you have K2 is equals to minus 6, K3, which is minus 6 over 5. All right. Then K1 remains arbitrary, R, but you can choose it to be 0. And here you are. Or if you wanted, you could have chosen K1 to be equal to 5. Then you would have your Q to be equal to 5 minus 6, 1, so that it doesn't have fractions. But here, okay, I allowed it to have fractions. Maybe I'm comfortable working with fractions. So then we now have this. And we then assemble now the three linearly independent solutions. K is the power lambda 2, KT plus P, and then we have KT squared over 2 plus PT plus Q, and so forth. So you can see that we now have three linearly independent solutions, or solution vectors associated with these repeated eigenvalues, and the solution becomes longer like this. So that's how that's how you do it. That's how you do it. That's how you do it. I will stop here and then deal with the case of complex eigenvalues in a different video. Thank you.